Good morning, everyone, and welcome to the lesson recap for Adaptation Strategies Lesson 3, where we focus on a landscape scenario modeling. Janet's out today, hard at work on the challenge that you guys will be receiving in a couple of weeks. And so it's just us today to talk about landscape scenario modeling, but I'm pretty excited about it because that is the focus of my own research. So I know there's a lot of terminology that comes with talking about landscape scenario modeling. And so we had some questions that came up in the Muddiest Points about that kind of stuff, and then how we apply, how do we choose models. And so I hope that I'll be able to answer some of those questions in the recap. And if anything is still muddy after you've watched that and maybe gone back through the transcript and dug in a little bit more, send me an email or we can schedule time to chat so that everybody's kind of crystal clear on moving forward in this. You'll get a chance to use some scenario analysis in lab this week, and then we'll have an activity for those of you who get to come in on Thursday to work in discussion together. So I'm looking forward to that. Let's jump right into the PowerPoint. Thanks everyone for completing the online lesson for landscape scenario modeling, and now I'll try to address some of the points that maybe weren't clear to everyone while they were going through the lesson. In topic 1, we provide an introduction to models, and there's a lot of terminology that comes along with talking about models. And so we want to go over in the recap what static versus dynamic modeling means, as well as what deterministic versus stochastic modeling means, and which of these kinds of models are useful to answer what kinds of questions, or how do you choose between deterministic versus stochastic modeling. We also walked you through one tool for landscape scenario analysis called TELSA, or Tool for Exploratory Landscape Scenario Analysis. We'll go a little bit more in depth in sort of what TELSA looks like in the recap so you guys have an idea of what that interface might be. In topic 2, we're going to provide another analysis of scenarios, or how you could use scenarios to answer landscape ecological questions. And then in topic 3, which is about applying scenario modeling, we'll delve deeper into how we can choose our model, or the kinds of questions that we need to answer in order to help us to identify the right model for our purposes. Static versus dynamic modeling. Static modeling describes relationships that are often constant and lack a temporal dimension, so time is treated as static. They often use empirical data or data derived from expert knowledge to determine or estimate the relationships between different elements and then apply those relationships more broadly. So the example that we've already explored earlier in this module is habitat suitability modeling. And so basically in habitat suitability modeling, time is static. You have one snapshot in time, and the landscape is static. You have one land cover data set, right? And that land cover data is not changing as you in your model. Basically what you have is you might have presence absence data, that you have other attributes that you can start forming a relationship of how an individual species might choose the particular land cover types in that landscape. And so that's an example of static modeling. There are just fewer changes incorporated into your model. Dynamic modeling, on the other hand, represents systems or phenomena that change through time. So in a dynamic model, there's an interaction or series of interactions, often involving some sort of movement, associated with each phenomenon at each time step. So we might think of species dispersal or migration models as an example of dynamic modeling, where you start out with a particular starting point where you have these species distributed on the landscape, and then based on other data that you have, you might model how they move through that landscape, like we did last week. And so that is dynamic modeling. Land cover and land use change models are also dynamic models in that they simulate from one time step to another how a particular phenomena might change on a landscape. There are two kinds of dynamic models, deterministic and stochastic. A model is deterministic if the outcome is always the same once the inputs and parameters and variables have been specified. In other words, deterministic models have no uncertainty or variability and produce identical results for repeated simulations of a particular condition. A model is stochastic if there's an element of chance affecting the outcome given any in the set of inputs. So the same input conditions can result in different outcomes for every simulation. And most landscape models are stochastic, but one of the questions was, well, why would we want to use a deterministic model over a stochastic model when we know that a lot of natural processes are stochastic? And so oftentimes, when we're doing landscape modeling, we want to understand how particular elements of a system interact. So we might want to understand interactions between management activities and wildfire, or we might want to understand interactions between the movement of one species and logging. And so being able to hold particular inputs constant or in a deterministic way allows you to add and remove different elements from that model and understand how they interact. So that's where we might want to identify the most important landscape processes for further study or do a sensitivity analysis. What happens if you change just one metric in a particular way, and how does that change those relationships or how the landscape responds? You can also use it, this is also a way to understand the implications and interactions of specific assumptions and hypotheses and pattern and process. So if you don't have random chance, you can purposefully vary elements in your model to see how the outcomes behave. And so that can help you better understand how a system works. And so that's when deterministic modeling is really useful. Stochastic modeling, on the other hand, which does incorporate these elements of chance, that does more realistically simulate patterns and processes on a landscape. And it's useful in making predictions about future ecosystems or landscapes. It can help us understand complex systems that'll account for spatial processes and dynamics over long timescales. And then you can start to explore real or hypothetical scenarios. You can also do scenario analysis with deterministic modeling, but stochastic modeling allows us to sort of use this element of randomness to our advantage. Often with stochastic modeling, then, you repeat a simulation several times, which is called Monte Carlo iterations. So you run the simulation many, many times, and then you try to understand the natural range of variability in that system based on this randomness. And so you get bounds for particular outcomes rather than one specific outcome. So we're going to explore an example of stochastic modeling when we talk about TELSA, and then we're going to move on, and we're going to have another example that we didn't talk about in the lesson. So another example of scenario analysis comes out of Nassauer and Corey's lab, and the study was from 2004. And basically, they proposed alternative scenarios for a federal agricultural policy, and tried to understand how different alternatives would affect the watersheds of their study area in Iowa. And so basically, they have three alternative scenarios that emphasize different ways of managing the landscape or different agricultural policies. And so what they did is they started a discussion with people in this landscape, and they started designing these envisioning workshops and interviews. They started designing these narratives or these particular alternative futures that might come out of different agricultural policies in this landscape. They used GIS and maps. They used particular landscape metrics to analyze and quantify the differences of the landscape between alternatives, and then they brought them back to their user group. So we can see here that this is their watershed that they were interested in Iowa and present day, which was in 2004. They had the first alternative scenario outcome, scenario 2, and scenario 3. The darker a particular unit appears in this map indicates a greater level of water quality benefits for that area. So you can see in present day, the water quality benefits are really concentrated around this particular drainage, Whereas in other scenarios, you get a distribution of those benefits more broadly on the landscape, but most of the highest benefits are still very closely related to that particular waterway. And in the alternative scenarios, you can actually start getting much, much greater benefits further and further from this central drainage, depending on the conditions of that scenario. So that's just another way to use scenario analysis. It doesn't necessarily have to be to do with species conservation or land cover, but it might be to do with different policy alternatives, watershed benefits. The possibilities are pretty much endless. And we're going to ask you to think about that in the discussion question for today, so stay tuned. So the next question we have was about choosing a model, and how do we determine what model is right to answer our question? So there are a couple of guidelines here like we had in the lesson. And the first very important thing is to define your research question. And this is just like taking us back to the beginning of using GIS to answer a particular question. It's really important to specifically define your research question. And then you need to identify the biological and ecological processes that are relevant to that question. So do you need to incorporate time? Is it important for you to understand change over time? Do you need a deterministic or a stochastic model? Do you need to just understand how this system works, or are you trying to make predictions that capture ecological variability? Do you need to have a spatial model? Sometimes we don't need to have a spatial model to answer particular research questions. And then there's a myriad of questions that you could ask yourself, but really understanding your research question and what information you need, what processes are important to those. Once you have these particular model characteristics defined, you can start comparing models that simulate the processes that you need to incorporate. You can ask if the necessary data is available for each of those particular models. If you don't have the kind of data that might be necessary for a model, then you're obviously not going to choose that one. And you can also ask if they provide the kinds of output that you need. So are these models going to be producing spatial output if you need it? If not, then you might not choose that model, and so on. Sometimes you can dig through the literature or be working with particular kinds of modeling that you can actually find one of these model selection decision trees, or you can start creating one yourself. And so this one is actually a selection decision tree for forest landscape simulation models. And this was published by Scheller and Mladenoff in 2007. And so they start out by asking, do you need to include or exclude spatial interactions? Is that an important process for your model? Does one particular area, do you need to model the spread of fire, or do you just need to know if a particular forest stand is suitable for a species? And so you may want to exclude or include spatial interactions. Do you need the communities with the vegetation communities within your model to be static or dynamic? So is it okay if the vegetation communities are defined and the species composition doesn't change in a particular stand in a single time step? Then static communities is okay. If you need dynamic communities, in other words, if you need from one time step to the next, if you need the species to track the species composition change in a particular area, then you might need dynamic communities. And so you might choose models for static or dynamic. Then, are you including ecosystem processes like nutrient cycling? If you include or exclude those, you're going to end up with different models. So you can see in their decision tree that they had 8 total groups of different simulation models. And so these are different models that are specific to forest landscapes. And some of them you can actually apply in other kinds of landscapes. Like IBIS you can use for agriculture sometimes. VDDT Telsa you can actually use for a wide variety of landscapes. Landis, on the other hand, is very attuned. Landis 1 and Landis 2 are very attuned to forest landscapes, as is Harvest. So you can start digging into, once you've sort of identified these categories of decisions of processes you may or may not need, and you come to some models that you're interested in looking at, that's when you can start asking, do you have the necessary information to run those models? Are they going to produce the kinds of output that you would need? So state and transition modeling is one specific kind of modeling that we introduce you to in the lesson, and so that's TELSA. So TELSA is a state and transition model, and the definition of state and transition modeling is that a particular ecosystem, and let's say that that ecosystem is one cover type, so that's the northern hardwoods land cover type or ecosystem in this case, and this ecosystem is divided into specific states. So each of these boxes represents a specific state of that ecosystem. In this case, it's different successional classes. So for each successional class, there's an age range. So for this early one successional class, the stand can be 0 to 10 years old. And there's a particular structure of that state defined, which is canopy closure. And so this is all. So that means it's mixed canopy closure. In a single stand, you might have some very open areas, and you might have some very some closed off areas. In contrast, there's this late one state, which is very old. It's 101 to 99 years old, and its canopy is closed. So once you've defined each particular state, then you define transitions, or how a stand could move from one box to the next. These green arrows represent transitions, the growth of a stand, which is just aging up of from one state to another. So when the state ages from 10 and grows to 11 years old and moves on to the next box or the next state. And these blue arrows represent transitions from natural disturbances or management activities. And so you can see that these probabilistic transitions down here include fire, wind, selection cutting, and so on. Each of these transitions is assigned a probability of occurrence. And so when you run the model, it draws from a probability distribution that particular transition type would happen to that particular state during that time step. And so we can see, for instance, the probability of fire is very, very low. It looks like the probability of it happening is like once every 2,000 years you might have a fire, and that's pretty common for northern hardwoods, which are kind of a fire-resistant cover type. So in state and transition modeling, you might develop these models for a different model for many land cover types on a landscape. You might have 8 to 10 land cover types in your study area. And each of these models has lots and lots of documentation. So they were developed by Landfire, and they each have documented who the modelers were and who the reviewers were for this particular model. For instance, you notice Randy Swati was one of the reviewers for the Northern Hardwoods Forest model. There's a geographic range description. It describes the vegetation classes and all of those probabilities. And this documentation is actually really, really important for modeling. For each cover type, you really want to be able to describe everything someone would need to know to track down who to ask a question to, or to know where that information came from, so they can discuss how reliable it is and feel confident that the model is actually going to be accurately describing their system. So, like I said, who contributed to the model, the geographic range in which that model is applicable, the biophysical nature of the site, the vegetation, the disturbance descriptions. Does this cover type overlap with others? So, for instance, if you have nature is very dynamic, you have lots of gradients, and one cover type there's not a hard line between one cover type and another cover type, there's often a gradient. And so we want to know, are there gray areas in this model? Are there areas that might be better captured by another model, or where they have overlapping ranges? Are there other issues or concerns with the model? And then any comments the reviewers think that modelers might need. And so again, you could just go and look these up on the Landfire website. We can see that we're in map zone 50 over here, and you can start downloading and looking at the models and their descriptions in TELSA. Someone asked if we could use TELSA in our, we're not going to be using TELSA in lab, but if you want to poke around with TELSA, it's VDDT and TELSA are free programs that you can download. And VDDT is the Vegetation Dynamics Development Tool where all of these state models were actually created in. So once you have all of your state and transition models, basically definitions of how those cover types work, you want to start capturing the spatial nature and the variability or stochasticity of those cover types. And so in TELSA, you can start talking about, for instance, fire disturbances. You develop the size class distribution. So you say, so here, 68% of fires in this landscape are 1 hectare or less, and then 27% are between 10 and 1 hectares, 4% are between 100 and 10 hectares, and so on. And so that's sort of the size class distribution. What the model does is every time step, if a particular stand is going to be affected by fire, it randomly draws from this distribution. So this is the probabilities that that particular fire will be of these sizes, within these size ranges, but it randomly chooses the size of fire. You could also have it randomly choose where on the landscape that ignition happens, and that's based on sort of the return intervals of fire in different, or how flammable essentially different cover types are. And so then you have to add the spatial data to this model. So we start out with the vegetation map, which is the veg map. The tessellated veg map actually breaks the landscape up into tiny, tiny, tiny pieces, or creates stands, which are the sort of minimum unit that a particular disturbance can affect. And then we overlay the PZ map, or the planning zone map, and that allows us to define ownership. So management activities might vary by ownership, for instance, and so we want to be able to capture that in the model. And so then you start combining these different maps to create different scenarios. So if you have more than one arrangement of ownership on that landscape, then you could combine your vegetation map with one ownership and run your model for scenario 1. And then you can combine the vegetation map with a different ownership and run your model for scenario 2. And that allows you to sort of start creating different possibilities for this landscape that you can compare the outcome. So within each management zone, you can define, like I said, you can define different management parameters. So for every cover type, we have particular activities that are defined on the landscape. And so for clear cutting, you can have in boreal acid peatland, this is the age range that the stand has to be in, and then this is the entry size. And so this is another element of stochasticity. So that the particular entry, or that particular harvest in a single year, has to fall somewhere within this range, this minimum and maximum. But that too is a stochastic part of your model. So then to create your ultimate scenario, you define the spatial scenario, which is the combination of vegetation and planning zone. The transition rules, or that basically defines those management transitions for each of your scenarios. You can also vary your natural disturbance transitions for the different scenarios. So you could, for instance, you could ramp up fire, the probability of fire, if you're looking at trying to model a scenario in which climate change has resulted in a very, very dry summer season and a longer fire season due to shorter winters and less rainfall. So the probability of fire might increase, and that could be another one of your scenarios. Then you can choose the activities in the sort method, so which activities do you perform first, and all kinds of different ways that you can set up the spatial nature of your scenario. So for this discussion question for this week, we would like you to think about how you might use scenario modeling in your own work. So what kinds of scenarios might you develop to answer a particular question, or what question in your work lends itself to scenario analysis, and then what kind of model would you need to simulate those scenarios? And so remember, this is when we're asking you to sort of go back and choose a kind of model. Does it need to be dynamic or static? Does it need to be stochastic? And so remember to use the modeling vocabulary when you talk about what kind of model. You don't have to identify a specific model, but just what kind of model would you need, what kind of processes would you need to simulate in order to model the scenarios that you might use in your own work. So I'm really looking forward to reading those and participating in those discussions. And like I said, we're going to be having an activity on Thursday's discussion this week about landscape scenario analysis. So I'm looking forward to seeing you guys in lab and in discussion.